Welcome. Chemistry in the AM. I'm Joel Sindel. We're starting on our titration portion. We're jotting down these notes, pause the video, and jot them down as well. Titration, acid-base neutralization reactions. The definition is a salt. That's a substance formed when the cation of a base combines with the anion of an acid. They generally have about a neutral pH. Now, we think of table salt when we say salt, but form other salts. They're ionic compounds. How to write these acid-base neutralization reactions? In general, an acid plus a base will give you what we call a salt in chemistry and water. If the salt, remember that the salt formed is a combination of the cation of the base and the anion of the acid. That's a repeat. Okay. Now, I'm not going to get you to write the next part down. That's why I covered it up. I'll pause here for a second. So here's what you're not going to write down. These are the directions, though, for the next portion. Right. So we're going to write a non-ionic, a total ionic, and a net ionic equation. Three things we'll learn to do by doing for neutralization between the following. And we're going to identify the acid, base, and salt. I'll just erase the actual answers. Your ink. Okay, good. Sulfuric acid, sodium hydroxide, nitric acid, calcium hydroxide. We'll do these two examples. So, sulfuric acid. If you don't remember what it is, it's sulfate ion with H's attached. Turns out to be H2SO4, but you'd look that up on a chart. You have actually all the most of the acids that we use listed actually in your Ka chart too. So, sulfate ion H2SO4. Sodium hydroxide, it's Na with an OH minus. So, first thing, why? Sulfuric acid, H2. Plus sodium hydroxide, NaOH. It's a positive one, negative one, so that's just a 1-to-1. We use a single arrow. They're both strong. And the salt in this case. So, if you want, get rid of, I'm going to put the water over here, but I'm going to call it HOH. Because it makes it easier to think of for balancing. I've told you this before when I had you do this on the sun, H2CO3, I think. Take off one H at a time, one proton at a time. H2SO4, we're only going to remove one H. So that means remove this one H, right? What does it become when you remove one H? HSO4 with one H. Now, with the base, if it's a hydroxide, just get rid of the OH. You've got Na plus. What does Na plus do with the HSO4 negative? Like, what's the combination? Say it out loud. Maybe jot this down because it's actually part of this. This is the ionic equation, total ionic. Okay? I'll just wait for a second. Jot this down to me, okay? I'll just get some labels here. Acid, base. This is obviously the water, and we're going to have a salt. So, what is it then if the H and the OH come together to make water, right? You got Na plus and HSO4 minus. What's the formula? when they come together. Positives always come first. Cations come first. So the formula. NaHSO4. Okay. Now, here's something underneath here that I asked you to copy down, but I'm going to put in the 8 here. Okay, that's what we're just going to chat about. Okay. So what's happening here? The whole thing is that we know we form water, and from the acid, the H and the OH make water. And this is why I like writing water instead of H2O, HOH. You clearly see the front H, you can pick up from the acid, the OH, negative hydroxide. That happens. In this, the aqueous means an ionic compound and so on, acids together. They separate into their ions, they dissociate. And this is still aqueous on this side, meaning that really it's floating ions. It's Na pluses and HSO4 minuses on the right hand side. So, do some labeling. First of all, that this is the called a total ion equation. So that's what's below there. And that the sodiums are really just floating. But the water is a molecule. It's not floating around. It doesn't separate. It is just still water. If you want to write it as H2O, go ahead. I'm going to keep it as HOH. Same thing. Okay? So there's my total ionic equation. What we might notice is that there's repeats on the left and the right. They're exactly identical. HSO4, HSO4, Na plus, the Na plus. They're still in ionic form. Cation and anion. So really and truly, we call them spectator ions. They don't really do much of it, actually. What it is that H plus, the hydrogen ion, cation, and the hydroxide anion come together to make water. So the net ionic equation is as follows. Really, eliminate those underlying spectator ions. We really have that just H plus, OH negative came together to form water. This time you can keep it as HOH, you can keep it as H2O, it's the same thing. Okay? Like that. Okay, we're going to do this one together. So let's get a separation. A little fun here. I know. Okay. Nitric acid is HNO3 calcium hydroxide, CaH. Yes, I will. Now, arrow. I know that water's going to form. I'll put that on the right hand side. And this is one where it's really important that you think of it as HOH, because there's going to be some balancing. We'll see some. in a second, or a good scope. We're going to list the total ionic equation. I won't label it this time. The total ionic equation. That's an H plus hydrogen ion to a nitrate ion. Calcium. You can look these up on the chart. There's two groups of hydroxide. Now, this will be the last problem you have to do a total ionic equation. It's really just the thinking step. I want to show you how you should think of it. You don't explicitly have to write it. If it helps you, continue writing. You don't need to. Okay. We know that the H plus and the OH negative went to form water. So we've got calcium cation and nitrate anion to mix together. What is the formula when a calcium 2 plus and nitrate 1 negative come together? I'm asking you. I know the answer. I want you. Okay, Ca, we're filling this in here. CaNO3, well, we need 2 of those. It's going to be aqueous. Okay? That means for our total ionic equation that we have another group of Ca2, 2 groups of NO3 negative plus our water. And you're going to say, wait a minute, this ain't balanced, and it ain't. Now we're going to be doing some scratchy on the total ionic and scratchy. Let's balance the top equation. They both represent the same thing. More compact. That's the way we usually represent it. So I'm going to use green to do balancing. Think of it this way. Hydroxide, there's 2 groups. I'll use this green. There's 2 groups of hydroxide, right? So 2 groups of hydroxide must be here in the water, so I'm going to put a 2 there, right? That's how I think of it. I'm going to put 2 here, squeeze it in. At the same time, I'm going to just go back here. Put it on. Okay, now that means, you see why we did that? 2 groups of hydroxide, 2 groups of hydroxide. So that's the front. That screwed up the H plus, the hydrogen ion. HNO3 is only 1, so I need to put a 2 in front of nitric acid. That means I need to put a 2 on the total ionic equation. Okay. Do I have this balanced this way? Yes. Yes, it is. Now, like I said, we're going to do some scratching out. This total ionic, we want to get the net ionic. The H and the H plus, the hydrogen ion and the hydroxide ions made water. We know that now. But you notice that these 2 nitrates never change. They're spectators. This time I'm actually literally scratching. Calcium. Calcium. They didn't really change. What this tells us is that you add an acid in the water, the things that really matter is the hydrogen ion and the hydroxide ion. You add acid to base, because you form a salt and water. This part will always be the same. H plus, OH negative. This is our net ionic equation. I'm going to put it as 2H plus. I'm not going to reduce it. Yeah. Still balanced with 2. So that's our net ionic equation. And that's what I was just, want you to see that it's always going to form water. True. And this is why we will not continue writing the total ionic equation. I think of that as the thinking step. After this second example, I won't be asking you. That's a true example. You can see that basically, if I ask you for a total ionic or net ionic equation, given this, you say, okay, what's going to form the water, the H and the OH? Okay, this stuff, the H and the OH. And then it's the calcium and the nitrate that disappear. That's, it always ends up being that, with an acid base neutralization. Okay. Now, I'm going to you know what? I was going to give you guys some questions like this. Do you guys think you get that though, just from those two examples? Or do we need a practice question? You guys tell me if you're adults. Okay. We just did these two. So why don't we try hydrochloric acid, potassium hydroxide? That means you got to look it up. If you don't know what potassium hydroxide is, hydrochloric acid, I think you know that one. And then skip to the net ionic equation, which you already know is just going to form one. I'll pause the video, try example 3. That. Okay. On the video, I'm just going to post these in case you want extra practice. You can just zip to the video and take a look at these ones here. Hydrochloric acid, barium hydroxide, there's an answer. Hydrochloric acid, magnesium hydroxide. Here's an answer here. If you want those, pause the video and try those out. Now, what we're going to do, we're gearing up to do a lab. Now, I want to tell you about this. Don't take this down as notes. I just need you to listen as we go over this. Titration curves dry lab. We're going to listen because then we're going to do the lab. What happens to pH as a strong base is added to a strong acid is really what we're going to talk about. Now, if I was to graph that, you're adding to a strong acid. So a strong acid has a pH that's what? Compared to 7? 1, let's say. Okay, low. 1. And you're going to add base, which has maybe a 13, right? So it's going to climb and climb and climb. But does it climb? I'm going to just do this as here's the graph. A pH of 1 to start with, 1 down. Does it climb linearly? Does it make a curve? What kind of shape? How does it climb? This is what we're going to talk. Now, the thing about pH is, and if you know something about math, pH, remember, is the actual power of 10 that we're talking about. So every time you go up 1 pH unit, it goes up by times 10. It's not a linear measurement, pH going from 2 to 3 to 4. So when we graph things, it might be a little weird. So I'm going to just take a look at this data here. I'm not going to get you to copy this up. Oh, what did it say here? Oh, procedure. Let's imagine that we had in a lab decimal 1 molar sodium hydroxide added in small amounts to 50 mils of decimal 1 molar hydrochloric acid. And we're going to complete this chart as we add. So this is the chart. Now, it's got a bunch of writing on top. But here's what I'm going to end up. Oh, and I'm not going to get you to do this. So in a beaker, we started out with that many moles of HCl. That's not changing as you know, right? But then we start dripping in some sodium hydroxide, the base. So at the start, it's 100% acid, no moles of sodium hydroxide. So you have an excess of acid. And the pH is 1. We won't look at everything. Okay? This is, that's just guessing. Exactly. We add a little bit of sodium hydroxide, 0.01 moles, and I just show one calculation. Well, we still have way more acid than base, so 1.2 is. We add some more. Remember, we had 50 mils of the same concentration of acid. Now we have a 40 to 50 ratio. That's almost equal, right? We have a decimal 0.005 moles of acid to 0.004 moles of base. It's not too far off. But we still have a low pH of 2. Right? Then what happens is almost equal amount, 49. Well, the pH is still 3. This is the way to math. 49.9. pH is 4. Then one drop, you get to 50 mils equal amounts, acid, base, equal concentrations. There's no excess of acid or base. It jumps to 7. And then another drop of base, and it jumps to 10. Now it's in the base region. You guys see? There's a huge jump right around the neutral equivalence point. And when you graph it, this is really what the graph looks like. It tilted all the way to 40 before you had a real change. Pretty flat. It's slightly, but very slowly. Then it skyrockets within a few drops. I have 3 different squares or rectangles because we could use different indicators. I told you about indicators before. We used this one, I think, for almost time all through, where it went from yellow, green, blue, right? You remember that? And we'd add acid equilibrium. I didn't tell you about the acid base, but it would change colors, right? But you know me, I can't see colors, so I stuck to one particular indicator because it's on or off, color or no color, called phenolphthalein. You've seen this. That pinkish stuff, reddish pinkish, or clear and colorless. So I can tell that because it's off or on. And so I use that. But it really doesn't matter which indicator you use because it skyrockets within one drop. Some indicators actually have a pH range of maybe 8 to 10. Well, it doesn't matter because it just jumps right through that. Another one might be actually in the 7 zone. Another one might be from 5 to 6 or something like this. It doesn't matter. They're all going to give you the same result by within one drop. So they're all equal to that. And then it levels out after that. So it skyrockets with one drop, 49.9 to 50, and then it levels out. So the pH is not a linear change as you have. That's what I really want to get to. So we're gearing up for titrations. We're going to do a titration lab. We're going to use vinegar. But more about that when we get there. But I do need you to do this example with me. So just a second here. Here's what you need to copy out. I'll read through it first, then you can copy. Titration calculations, you need to copy that. Base balance times the moles of acid. Don't copy yet. Put your pen down, just listen. So BB stands for the balance number in front of the base. So when you in front of calcium hydroxide or potassium hydroxide, if it's a 1 or it's a 2, it's that number. This almost looks like the dilution equation, right? CAV. Well, that's the concentration of acid, and then the volume of it. Then the balance number in front of the base. So if I had a 2 in front of the HCl, if I had a 1 in front, if I have no number, it's a 1. Concentration of the base, volume of the base. That really makes the moles of the base. Now, so I'm going to read through this and I need you to pay attention. The point at which the pH is 7 is called the equivalence point. You have the exact same amount of acid to base. That point could be determined within a few drops of base solution. Because the pH changes sharply, you just saw it, that skyrocket. When the indicator changes color, and we'll use phenol-thick, the titration is said to have reached its endpoint. If the titration is done properly, the endpoint is very close to the equivalent, within a drawing. Now, what I want you to do is copy that first bitty and then the example. Okay? I just wanted you to listen as we went through. I'll pause and let people online talk. Away we go. Oh, this one too. I have to erase the thing. You need to scroll up again, just to... So the very first thing is calculate the concentration. Okay, I'll read the problem again. Nitric acid and barium hydroxide are added together. The first thing you need to do on any of these questions, even if it's not explicitly asked, is do the reaction equation, because you're going to need the balance. Plus, it's always given a mark. So I need to know what nitric acid is. We just used it in a problem, though. So HNO3. And it's important in this unit to use aqueous. HNO3. I'll leave space in case we need to balance on the next one. Barium hydroxide, Ba, 2 hydroxide. Reacts to form. Well, we know water is going to form, so that takes care of the H and the OH. That leaves the Ba2 plus and the NO3 minus. What is the salt that's formed? Barium, nitrate. Barium has a 2 plus charge, so you're going to need 2 nitrates. And then water. I'm going to put it as HOH to make it easier to think of the balance. I think of it as H plus connected to hydroxide. It's a liquid. Here, there. We're good? I don't know how to do that. That's why we package stuff first. Then we got to balance. And I think, oh golly, I got 2 hydroxides here, so I definitely will form 2 waters. Take care of 2 hydroxides. Now I've screwed up the H plus, the hydrogen, the protons, the H plus. So I need 2 acids. That takes care of the H plus. Now I've got 2 NO3s in that front acid, but we have 2 NO3s in the compound barium nitrate. So it's balanced. Equations and given information. Now, I won't normally ask you to write up the given information, but this is for learning, so I'm going to. So the balance number in front of the base is a 1, barium hydroxide. You guys know why we did that, right? That's the balance in front of the base. Then, the only other one I'm going to do the rest of the sentence is the balance in front of the acid. Is the 2 in front of the nitric acid. We see a green 2. Now, the rest, I'll just draw it in. 20 ml sampling of the acid. Well, that's the volume of the acid. Average volume of 55 mils of the hydroxide. So 55 mils is the volume of the base. We have a concentration of the base. We need to find the concentration of the acid. So we're going to use that equation. Oh, still have the answer up. I'm going to plug stuff in. Balance the base. I wouldn't normally write down 1, but I'm going to this one. Concentration of the acid is what I'm trying to find. The volume of the acid was 20. By the way, I didn't change this to liters. As long as the other volume is in milliliters as well, it's fine. Matching units. Balance of the acid is 2. Concentration of the base, 0.47. liter, and then the volume of the phase was 50. I have two significant digits. We'll assume the 20 is 2. Mathematically, that's not tough. We divide by 20 mils. Get a concentration of the acid. Decimal 2 moles per liter. And that acid, we actually know it, so I'm going to label it. Ca is HNO3. Okay? There you go with an example calculation. What I'm going to do is hand out titration example questions here for you guys to do, and yes, I'll be taking these out. So I'm going to hand these out. You'll self-mark them, but I'm going to get you to report to me about them. And we'll get ready for a lab tomorrow, but we'll be doing the lab next week, okay?